Hello, in this video I'm going to do a couple more examples of linear programming using the graphical technique. So remember, a linear programming problem always has some type of an objective function. In an example 2, the objective function is p equals 10x plus 25y, and we want to maximize that. In other words, find the maximum value of p, which I like to think of as profit. It doesn't necessarily mean profit, but it's just an easy way to think of P as for profit, something that we want to maximize. The objective function is subject to the constraints 5x plus 2y is greater than or equal to 40, x has to be less than or equal to 10, y has to be less than or equal to 15, and then we have the non-negativity constraints. Now, I usually don't graph these. X is greater than or equal to 0, and y is greater than or equal to 0. We just have to remember that we're working in the first quadrant in the Cartesian coordinate system. X's have to be positive, y's have to be positive. So let's go to Desmos, and I've already entered, for convenience sake, entered the equation is in here. And if we just take a look at the first equation, we can see the line and the proper shading. And then I'm just going to click on the second one, x is less than or equal to 10. And so the overlapping area that is shaded both of these is this narrow wedge going up through here. And so finally, we have y has to be less than or equal to 15. And so now the overlapping shaded area that's shaded from all three of these is this area right in through here. Now, we also have to keep in mind that x has to be positive and y has to be positive. So if we enlarge this area a little bit, this is our feasible region in through here, but notice that it goes down below the y-axis. We can disregard that. We're only looking for the area where x and y are greater than 0. So I'm just going to enlarge that area a little bit. So our feasible region is this region in through here. All right, so that's the first step. The second step is to find the coordinates of the corners. So remember, the feasible region represents the solutions. Any value, any x and y ordered pair in the feasible region will satisfy all of the constraints, including the non-negativity constraints. However, the fundamental theorem of linear programming says that the optimal solution in the feasible region will always occur at a corner point. So instead of trying to figure out which one of the infinite number of ordered pairs in the feasible region gives us the maximum solution to the objective function, we only need to look at the corner points. Makes it a lot easier. So if you click on this line, y is less than or equal to 15, you can just scroll over, and we have 215 as one corner point. Another corner point is 10, 15. Click on this, 10, 0, and of course 10, 15 again. And click on this line, 8, 0 is another corner point. So we have our 4 corner points, 2, 15, 8, 0, 10, 0, and 10, 15. So on my, here's a look at the graph, and then here are our corner points put into a little table, 8, 0, 10, 0, 10, 15, and 2, 15. And so what we want to do is substitute the x and the y values into the objective function for each one of these corner points. And so 10 times x plus 25 times y, 10 times 8 plus 25 times 0 gives us 80. 10 times 10 plus 25 times 0 is 100, etc., etc. And so we end up with our p-values. And since in the original problem it said to maximize p, we want to look for the largest p-value. And clearly the largest p-value is 475. So the optimal value of the objective function is 475. Now, sometimes you're asked, where does that occur? It occurs at the point 10, 15. The x value is 10, the y value is 15, and the actual optimal value is 475. When we get into doing word problems, these values for x and y will have meaning. They will represent something. So we need to be aware of all three of those values. The next problem I want to do is going to be an unbounded problem. So an unbounded problem simply means that the feasible region is not completely bounded. And so if you look at this example here, we have this blue line represents one of our inequalities. This line from A to B would represent part of our inequalities, and over here. And so there's nothing bounding this up at the top. There's nothing bounding it over on the right. The feasible region just extends upward and to the right infinitely far. And so what we want to do is we want to create an artificial bound. And so to create an artificial bound, we're simply going to create a horizontal line somewhere on the graph that will bound it on the top and create a vertical line that would bound it on the right. And I'll demonstrate that in the next problem. So we want to minimize c equals 3x plus 2y. Now notice that we are minimizing, and we usually use c to represent a minimization problem. And the way that I remember that is C for cost. Cost is something we want to minimize. So whenever that you see a C equals something, that usually is going to be a minimization problem. So just think of it as cost. We're going to minimize cost when we have the function 3x plus 2y, and it is subject to the constraints x minus 2y is greater than or equal to 0. Y is less than or equal to 100, and x plus y have to be greater than or equal to 210. And of course, we have our non-negativity constraints. X is greater than or equal to 0, and y is equal to greater than or equal to 0. So let's go back to Desmos. And I've already entered in these. So we take a look at the first inequality, and then y is less than or equal to 100. And we get that. So the common shaded area is down here now. And then the third one. And so now the common shaded area is all of this area in here. Our feasible region is all of this area. Except, don't forget, x has to be greater than or equal to 0, and y has to be greater than or equal to 0. So we only want to consider positive y values, so don't take anything below the x-axis. So this area in here is our feasible region. But notice that the feasible region is not bounded. It just goes infinitely far to the right, off to the positive x values. So what we need to do is we need to bound it somehow. So I'm going to put in, so it's bounded on the top by this line right here. It's bounded on the bottom by the x-axis. It's bounded on the left by this line and this line, but there's nothing bounding it on the right. So I'm going to put in an artificial bound, and it can be a vertical line anywhere past this point right here. Okay, any of our corner points we want to make sure are included. So this point, and this point. So if I go past, let's just make it easy. Let's go to 300. So I am going to put in x must be less than or equal to 300. All right. Now, that's an artificial boundary. So now our feasible region is this area in here. We are now bounded on the right by x is less than or equal to 300. And so we have a completely bounded feasible region. The next step is to find our corner points. So click on any one of the lines. So we have a corner point 200, 100, 300, 100. Now notice that 300, 100 is also a corner point created from the artificial boundary. It's not the real boundary. And then we have 300, 0, and then we have 210, 0, and 140, 70. And so let's go to and here I've put all of the corner points into a table. And again, you don't need to make a table, but it's helpful. And here's my objective function. And so we insert all of the x and y values in each corner point into the objective function. And so we are looking for the smallest value, because remember now, we're looking to minimize. That means we want the smallest value. So the smallest of all of these C values is 560. So the optimal value, which is a minimum value, is 560 and occurs at 140 and 70. And that is the answer to that problem. Now let's just do a little thought experiment here. Let's pretend in this problem, instead of saying minimize, it said to maximize. Right? So we want to maximize. We don't need to do anything differently. We graph it the same way. We make our table the same way, except now we are looking for the maximum value. So the maximum value here would be 1100, but there's a catch. Because 1100 is the maximum value, which occurs at 300 and 100, and if we go back to our graph, 300 and 100 occurs at one of our artificial boundary points. In other words, it's not the real boundary point. So if your optimal value occurs at an artificial boundary point, which this one does, then the answer is that there is no answer. All right. So that's also explained in my notes. Make sure that you read that over. But it's important to remember that if your optimal value occurs at an artificial boundary point, something that you created, then in reality there is no solution. All right, I hope you found this video helpful. Have a good day.